Yeah. In the meantime, before we get started, while we're waiting people to join the stream, are there any questions about the class, about the logistics of it, about homework 0, perhaps about the difference between 400 CSE 446 and 546? Any lingering questions on those matters?
And questions, just making sure everyone has managed to sign up for Gradescope and Piazza and has found, presumably your presence here means you have found your way to Zoom via Canvas, but please feel free to ask us any questions. We just want to make sure that you have those various things in place. I'm seeing some questions about how difficult homework 0 should be for us. I think the way we are treating this is that most of the material on homework 0 should be a review. You might have to remind yourself what some definition is, but it should not be a hugely difficult problem set for you.
Yeah, to follow up on that, I would say nothing should be new. It should be it's okay if you're looking at the problem, you're like, oh, right, I remember that from that class. Oh, how did that work again? And then you have to go back and look at it. But if you're seeing concepts on there that are completely brand new that you've never seen before, that should be concerning. And in terms of how difficult, I'm saying that, yeah, you might have to go back and look at things, but by the time you sort of reviewed the material and look back at these things, you should be able to, look at the problem oh, okay, yeah, that's how you do that, and kind of work through it in your head. Maybe you have to sketch some stuff on a napkin or something, but I should not imagine that these problems should give you a lot of trouble. But it's been a few years for a number of you. We're cognizant of that. A lot of you took linear algebra in your first year of undergrad, and for some of you, you're taking this as a graduate student, and you haven't seen that stuff in 4 years. So that's totally expected, that it's not completely fresh in your head, right? But you did take that course. You are responsible for it. So we expect you to go back and really review those materials. And that's what homework 0 is. We want you to get to the point where you can do homework 0 and be comfortable with all the concepts on there, because it is it's a barometer for how you'll do in the class. What was the mathematical maturity that you'll need to do well in the class? And if you can do everything on that problem set, then you should be pretty fine.
And I think Kevin made the remark last time, and I just want to reiterate, for each of the prerequisites that you're really uncomfortable with or you don't have, you should expect the class to take roughly an additional 10 hours per week, right? So homework 0 should give you some sense of just how quickly you can regain any information you've forgotten. If it's really taking you a long time because you're really having to delve back into the textbooks from your previous classes, not just for a quick review, but for more substantial stuff, that's indication that future homeworks will also be a lot harder for you than if that's not the case.
That's right. Is there any question on further questions on that?
It does seem like Piazza's been quite active for the first 2 days of class, so that's great. It seems like people are already starting on homework 0 and have started doing all the things you asked, so that seems great.
I see a question whether section 5, those in 546 going to section, and if they do go and be a fly on the wall, is there a preference on which section they should attend? No, whatever is just convenient for you. Section is not recorded, so this is not something that you can watch any one later. You kind of have, whatever works best for your schedule, I'd say. Kevin, are you hiding your own video on purpose? So, okay, yeah, maybe I should be more clear. Or transparent. I am having 2 Zooms right now. If you look through the list, Kevin Jameson is listed twice. The why is because I have an iPad and I have my laptop. My laptop is streaming my face and me, and my iPad is streaming the content so that I can write on the slides like this. Because that is how I will be lecturing, is basically writing on top of the slides. And so you to see my face, you'll have to go look for me in the other one of the other participants. So I am screen sharing with Zoom directly. That's how this is working. The issue is that if I just share my video from here, you'd be looking at the ceiling because my iPad is flat, and you would not be seeing me, and I couldn't see you on my laptop screen. That's why I log in on 2. An estimated time in homework 0 compared to time in other homework about equal? No. Homework 0 is not going to be an equal or representative of any other homework. That's why it's called homework 0 and not homework 1. You should not take away that homework 0 is representative of the amount of time or difficulty or content of the course. It is nothing more than a barometer of how much of your mathematical sort of readiness for this course. You should expect, one student say, if homework 0 takes 5 hours, should we expect the other homework to take twice that or more? More. I would expect, we're going to have homeworks due every 2 to 3 weeks. It would not be unreasonable to be spending 20 to 30 hours on the homework.
I do see some concerned looking faces, and I can't tell whether those are morning faces or faces that seem particularly concerned by that. We are trying to be conservative in our estimates for you. If homework 0 is trivial for you, we can't really predict how long all these homeworks are going to take for you. But this class is meant to be hard, at least in the sense that there's a lot of difficult material that you'll need to capture. Right? And we were very liberal with letting everyone in off the wait list, with the thought that would basically, that we would have to be really explicit about just how much work and mathematical maturity is expected for the class.
Yeah, we're not trying, it's not our intent to scare you or stress you guys out. We just want to be very straightforward. We don't want you to be surprised later on. And so this is why we're really kind of, we give the homework 0 and we say that yes, this is not going to be an easy course. That's it. I see a question here. Have professors listed your office hours yet? Sorry, no. We'll do that right after class. They're not on the website yet. Any last questions before we get started? And by the way, we are intentionally in these first 2 days, on Monday and today, we're intentionally getting kind of a late start because, people have technical issues. I had a technical difficulty getting my iPad connected this morning. We're just sort of working out the kinks. But, once we get up full steam, starting Monday, we will we'll be starting on time.
Yeah. So
I'm just trying to be very liberal with.
Yeah. Please join 5 minutes early in case you have any technical difficulties, because we will be starting right on time.
Okay, we'll go ahead and get started then. Welcome back. And today we're going to talk about basically your first learning algorithm. Over the course of this course, You're going to be learning lots of algorithms, lots of analysis techniques. And this is going to be the first one. We're going to be basically starting with the simplest, basic sort of estimator. This is kind of at the foundation of statistics, because machine learning really is, as we discussed, this beautiful marriage of statistics and algorithms and computation. And so today we're starting with a very simple estimator. Everything is going to be mathematically pretty simple and nice. And then as we get more sophisticated, as we look at more sophisticated algorithms, we will start looking in estimators. We'll start getting more and more sophisticated with our algorithms that are going to be used for estimation. But we want to get everyone on sort of the same page with a concept that is sort of universal and will be used throughout the course. So we'll go ahead and get started. So today we're going to talk about maximum likelihood estimation, the MLE. It's a fundamental topic in classical statistics and will be useful for everything. So let's start with a little scenario. Suppose a billionaire comes to you and he has a coin factory. He builds coins and he's trying to determine if the coins that he is creating are biased or not, right? These coins that his factory is outputting, what is the probability of heads of any given coin? And so then what we'd have to do is say, like, okay, we have for any given one coin, let's say he just picks one coin out of the bag. If I flip it, what's the probability it will be heads? Okay. So suppose we do this and we get something like head, head, tail, head, tail. Okay, we flip it 5 times. So flip n equals 5 times. And we see this sort of outcome. We see a head, a tail, a head, a tail in that order. So, and now if you want to get some estimate of like, well, what's the probability of heads of this coin? Then the most reasonable thing that you might estimate is like, well, I think this is actually going to be just because I saw 3 heads out of 5 tosses, I'm going to estimate that the probability of heads is 3/5, right? Because I saw 3 heads out of 5 total flips. So k equals 3 heads out of n equals 5 flips. But the billionaire very understandably asks, why? Why are you telling me 3/5? Where does that number come from? And how do you justify it? How accurate is that number? And so that's what we're going to go through today. So just as we talked about sort of this first lecture last time, machine learning really has, 3 basic concepts of you observe some data, you have some hypotheses about how that data was generated, and then you're trying to make predictions. And you're trying to make predictions on future data that's drawn from, say, the same distribution, but data that you've not seen before. And so this is analogously, we have, in this particular setting, we saw some sequence of heads, heads, tails, heads, tails, or whatever, some sequence of coin flips. We're calling this our data D. And we're saying that we observed k heads out of n total flips. And so our hypothesis about how this data was generated, we have to have some sort of hypothesis about how the world works. And the model or the hypothesis that we're putting on this data that we observed is that for each one, we said that each flip was completely independent of one another. So that means that if xt is in 0, 1, denoting the tth flip, then independence means that the probability that xt is equal to A and xs is equal to B is equal to the probability that xt is equal to A, probability that xs is equal to B. very explicitly, what this means is that the probability, given that xs is equal to b, that has no impact on the probability that xt is equal to a. They're complete independent events. Okay? And identically distributed, what that means is that the teeth flip has the same exact probability of being heads as the s flip for any t and s, for any two unique flips. And so all of it's saying is the probability that xt is equal to 0 is equal to the probability that xs is equal to 0, for example. And what we're saying very explicitly is that our model is that there exists some theta, some unknown probability theta, some theta in 0, 1, such that the probability of heads is equal to theta. So the probability of xt is equal to 0, where 0 denotes a tail, let's say, would be equal to 1 minus theta. And the probability of xt equal to 1 would be equal to theta. And so if our data, let's just be very explicit about it. Let's say this was our data. Then we have that this is equal to probability of seeing a head, tail, given theta. So if we're given theta, that we're saying that the true probability of heads is equal to theta. And then what's the probability of seeing probably head, tail? Under these assumptions, using the independence property, this is equal to the probability of head given theta, probability of head given theta, probability of tail given theta, probability of head given theta, probability of tail given theta. But now we just count up the number of heads that we saw, the number of tails that we saw. And so we saw 1, 2, 3 heads. So that's theta to the 3, and 1 minus theta to the, we saw 2 tails, so to the 2. Okay? And so in general, we see that the probability of the data of any sequence of heads and tails flips, given some particular theta that generated that data, is equal to theta to the k, 1 minus theta to the n minus k. So this is saying under the model in which the probability of heads is equal to theta, and the probability of tail is equal to 1 minus theta, and under these IID assumptions, and where IID stands for independent and identically distributed, so independent and identically distributed, we have that the probability of any sequence of flips given theta really just breaks down to this very simple expression, which is just the number of heads that you saw and the number of total flips that you made. Is equal to just theta to the k has 1 minus theta to the n minus k. Okay. And so now I've just rewritten this expression from the previous slide that we've just derived. And now what I'm saying is this is for any theta. So this was given a particular theta. So I fixed some theta. I said, what is the probability that I observed a k heads out of n total flips? And that is this probability. Given a particular theta, this is the probability that I observed k flips out of, or k heads out of n flips. And what we say is that this is also defined as the likelihood. This is the likelihood of observing this data given theta. And now what we can say, we don't know what the true theta star is. There's some true probability of a head coming up theta star, or a head, a flip coming up heads or tails, and it comes up heads, the probability of a head is equal to some say theta star. We don't know that value, but we're saying, given a particular theta, the probability of observing this data, given that that theta was true, is equal to this expression. And so if we just have data, if we want to estimate what the true theta star is, what we say is we define the maximal likelihood estimator as the value of theta that maximizes the probability of observing that data. Okay? So this expression is the probability of observing this data given a particular theta. And now all we're going to do is we can think of this function as a function of theta. So we think of this likelihood function. We're going to call this likelihood function because the probability of observing this data given theta. And we're going to think of this as a function of theta. And now we're going to search over all possible thetas and choose the one that maximizes this function. Because we observed k flips of n, k heads of n flips. We don't know what theta is. We're trying to estimate what theta is. And so we define the maximum likelihood estimator as choose a theta that maximizes the probability of observed data. And I'm going to note this, theta hat MLE for maximum likelihood estimate. And it's just the theta that this notation argmax is saying, what is the theta, what is the argument theta that maximizes this expression? So if this expression is a function of theta, the argmax theta p data of theta is going to return a value of theta. And of course, the log is just a function. You know, it's a log of x just looks like this. It's a monotonically increasing function on the real number, on the positive real line. And so basically, if I'm trying to find the argmax of the probability of data given theta, that's equivalent to maximize the value that maximizes that is also the maximizer of the log of that function as well. Because all I'm doing is basically scaling the values. And so the maximizer of a log of something is also the maximizer of that something. And so this line is then justified because the log transform is just the function is just a monotonic transformation. The ordering of the function values do not change. And so what we have, and there's also a picture for describing this. If this function that we're talking about here, the probability of data given theta is a function of theta, we can plot it on 0, 1, right? Because theta is the probability of heads. So it can only be between 0 and 1. So we have the left-hand side is 0, the right-hand side is 1. And we have, if we observed, say, 3 heads and 2 tails, then if we plotted what this function looks like as a function of theta, you'd get something that looks like a bump. And you'd get a bump around the value you can show quite easily. You'll get a bump around 3/5. And so that is what theta hat really is. You're just writing down the likelihood of observing the data given a theta, and you're choosing the theta that maximizes this likelihood function. So if we have that our MLE is defined as the argmax of the log of the probability of the data given theta, why are we doing the log? Because it's mathematically convenient. Because the log of this quantity, because the probability of the data given theta is this disgusting thing. It's a product of things. And anytime you see a product of something, it's very convenient to take the log of it because now it's much easier to maximize or reason about a sum of things versus a product of things. Okay, is there a question? This question, where does the estimation come from? The estimation is the fact that you saw data, you saw k heads and 2 tails. And now what you're trying to do is you're trying to estimate what is the true probability of heads that generated, what is the true probability of heads of this coin that generated that data. The estimation is the estimating what is the theta that generated the data. There's some true theta star. We're using theta hat and estimator for that theta star. So when we take the log of this expression, we said that this theta k to the 1 minus theta to the n minus k is the likelihood. We take the log of it. This is very simply just going to be equal to something very simple, but we're trying to maximize it. And anytime you're trying to maximize a function, if you have any function sort of on the real line and it's continuous, we know that a function obtains its minima and maximum, whereas derivatives are equal to 0.
Kevin, one quick question. Can we call on Barrage? He put his hand up.
Yeah. What's up?
Yeah, so previously, so you said that, right, so you're assuming independence and like IID. So basically, does that guarantee you like a good set of sample like observations?
Yeah, that's a good question. It allows us to, by assuming that things are independent and identically distributed, it's the model in which we talk about how the data was generated. And what that allows us to do is reason about, be able to build an estimator, right? Because if we didn't make these assumptions, it would be difficult to even talk about what are we trying to estimate. Because suppose there was some adversarial situation where these coins actually had, I don't know, like some sort of like device in them or magnets in them or something, where like the billionaire was actually trying to trick us and could make it be a head anytime he wanted it to.
Mm-hmm.
Well, under that assumption, I can't really do anything. What does it even mean? It doesn't make sense to even talk about what is the true probability of heads of this coin. And so by making these assumptions, we're saying this is what we believe how the world works. And writing down these assumptions of IID is basically saying, what are these are somewhat the fewest assumptions that we can make, so that if we observe data, we can then estimate, we can basically define what it means to have a probability of heads. And so it's really just it's not so much assumptions that we need to be able to estimate what the probability of heads is. We're just being very explicit about what we mean when we say the probability of heads is equal to theta. So it's more definitions. It's usually we're pretty cavalier about what's the probability of heads. And I'm just being explicit about what that actually means.
Got you. Okay.
Apologies for my dog, Kaya. She's usually very well mannered. Okay. Now, okay. So now back to what we were talking about. When we have a function, when you have any kind of function, and you're trying to find the maximum of it, we know that a function takes its minima and maximum, local minima and local maxima, when the derivative is equal to 0. And so if you set the derivative equal to 0, then, and you solve for what these points are, then you'll find they'll either be minima or they will be maxima. And then you need to figure out which is which. For this particular function, you can show it's quite easy. We'll be talking about this later when we talk about convex optimization. This function has one unique maxima. Because it has one unique maxima, we don't need to worry about it. And we just need to find the derivative instead of equal to 0. So that's what we're going to do. So if we start with this guy here, this is equal to the argmax of k log theta plus n minus k log 1 minus theta. And this is just using the simple rule that log of AB is equal to the log of A plus the log of B for any AB greater than 0. Okay? And so if this final expression at the bottom of this slide is the log likelihood, to find the argmax of it, what we're going to do is we're going to take the derivative of this function, and instead of equal to 0, and then this function, we know, I'm telling you, that it has one unique maxima, and so that will be the maximum of this function. And it will be, we're going to call this, we defined it as the maximum likelihood estimate. So if we take the derivative with respect to theta, of this value here, that's going to be equal to k over theta plus n minus k over 1 minus theta, but then times the chain rule, we get minus 1. And to find the maximizer, we're going to set the derivative equal to 0. So we've computed the derivative. We're going to set it equal to 0. And we're going to solve for theta. How are we going to do that? We're going to multiply theta, 1 minus theta on both sides. And that'll give us the expression 1 minus theta k minus theta n minus k equal to 0. And then we see that the minus theta k, the minus theta k cancels the plus theta k, because you get a minus theta times minus k. And then we just have that when we solve for that theta, we get that theta hat MLE is equal to k over n. Okay, so all we've done for this very, very simple expression, for some of you, this could be very, very, I'm intentionally going very slow, just so everyone gets sort of the mechanics of what we're doing here. We're writing down, we wrote down our assumptions on how the data was generated. Given that model and our assumptions written down very clearly, we then define an estimator, which is this maximum likelihood estimator, which is the value of theta that maximizes the probability of seeing that data. And then once we have that estimator, we solve for it using, to find the maximum of this function, we had to find the max. We know that the maximum is achieved where derivatives are equal to 0. So we set the derivative equal to 0 and solve for theta. And so if we do that, then we achieve, when we go through these mechanics, we achieve this final value of theta hat MLE is equal to k over n, which is exactly what we observed in our first sort of guess that theta hat, this guess for what the probability heads was equal to k over n on this very first slide. And now we're sort of justifying how we got to that answer. So any questions before I move on? Does the probability of data given theta have a meaning when you take the log? So it's called the log likelihood. The probability of data given theta is equal to, is called the likelihood function, and the log of it is called the log likelihood function. Does it have a meaning? I mean, it's a quantity of interest in a lot of analyses. It does have a lot of, we won't need to know this for this class, but like, yes, the derivatives of this function, the derivatives of the log likelihood, is intimately related to something called the Fisher information, which is intimately related to the fundamental sort of ability to do estimation. So this log likelihood, yes, it does have like very fundamental meanings in statistics, but for our purposes, it's just the log of the likelihood function.
Hey, Kevin, there was a question of whether you can switch your audio to the maybe to the iPad or what you're using to write on, so that will show up for folks when you talk.
I'm sorry, can you say that again?
Yeah, someone asked if you could switch your audio to whatever you're streaming the annotations from, because I guess that screen gets maximized for people when it detects your voice.
Yeah, I kind of am, is the thing. I'm using the iPad right now.
I do think people are able to pin. It's if you scroll down to Kevin's face and you want to see Kevin's face on the side, you can either pin or highlight his video, which will it'll keep his screen share in the left with like a large screen and his face on the right. Try that and see if that fixes your concerns.
Yeah, sorry. This is we're still working out the kinks, obviously. And I realize that my video keeps going in and out. So let me switch over to a different Wi-Fi. I tried to have these like 2 different Wi-Fis. I don't know why. I thought that would be easier for some reason. But let's see how this works. But yeah, you should be able to pin this video. So because the iPad, I'm connected with my iPad and my laptop. I'm talking through my iPad and writing on my iPad. So it should be consistent, hopefully. Okay. So what we just found is that this estimator, theta hat MLE, is equal to k over n, exactly the answer that we all expected. We got 3 heads, and we flipped it 5 times, so we saw it 3/5. So because we flipped it 5 times, we got 3 heads, you're telling the billionaire that the estimate of the bias, or the estimate of the probability of heads is equal to 3/5. But now you flip the coin 50 times, and the billionaire says, I got 20 heads. And so then what you would say is like, well, okay, by the same equation, I put 20 over 50, and that's equal to 2/5. And this comes to a natural question of like, which one is right? Which one is more right? And this really gets to quantifying your uncertainty, right? Because these are not like intuitively, because you only flipped a coin 5 times, this is going to have a lot more sort of variation. If I do this 5 times, I'm going to see stuff all over the board. But if I flip a coin 50 times, I trust that answer a little bit more. And what does it mean to trust that answer a little more? And so we're going to go into justifying this. These slides are supposed to be segmented. I apologize. So we know that if we flip a coin n times and we see k heads, we have that theta hat MLE is equal to k over n. But what we should know, one thing that's really important to check is, how good is this estimate at all? And one way to check that is saying, is it unbiased? So if I do this many, many times, what is the expected value of this estimate? Right, and so let's think about that for a moment. What is theta hat MLE? Theta hat MLE is really equal to 1 over n times the sum of t equals 1 to n, where t is the tth trial, of, say, the indicator that xt is equal to heads, let's say. Okay, where xt is the in heads or tails, denoting what is the teeth trial. When I flip for the teeth time, do I see a head or a tail? In this function here, for any statement omega, so if omega is an event, then the indicator of that event is equal to 1 if omega is true, and 0 otherwise. So this indicator here inside this sum is equal to 1 if the teeth trial is equal to heads, and it's 0 if the teeth trial is equal to tails. Very simple. And now, under our assumptions, there is some true theta star out there that is the probability of heads. So by assumption, there exists a theta star such that the probability that xt is equal to heads is equal to theta star by assumption. And another way of writing this, the probability of xt is equal to h is actually just the expected value of the indicator that xt is equal to h, because obviously this is just equal to the probability that xt is equal to h times the indicator that xt is equal to h plus probability that xt is equal to tails times the indicator that xt is equal to h. Right? I'm just writing out the expectation explicitly. And of course, we have that the xt cannot be h on both of them. And so we have that, sorry, let me redo this. Oh, that's my nightmare. Did not mean to do that. Okay, we're not gonna, so you can write the probability of xt equal to h as the indicator, the expected indicator of xt is equal to h, and you can prove that just by printing out the expectation, just doing it out explicitly, where xt, the true value of xt can only be equal to h, or it can be t equal to t. You write out all the cases. And so what we're saying is the expected value of theta hat MLE is equal to 1 over n. Expectations are linear. Expected value of xt equal to h. And then this is just equal to, of course, it's irrelevant, theta star. So we just get equal to theta star. And so this is a very trivial computation. And it's almost like hard to write it out because it's so trivial. But all we're saying is that the MLE for this case is unbiased. This means that if we repeat this trial many, 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 many times, if we flip this coin 5 times and see 3 heads or whatever, and then we compute theta hat, in expectation, we did this many, 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 many times, what is the bias of our estimator? And what we're saying is, on average, the expected value of our estimator is equal to theta star. That is not always true. And we will see many cases in this course where that is not true explicitly. But in this case, we have an unbiased estimator. And now, but this really just describes how happens on average. And if you like, you might have been taking your temperature lately, and because of COVID-19, and you might be recognizing, we always talk about 98.6 as being the human temperature. You might also be finding that if you take your temperature every day at the same time, and you do this for a long time, your temperature is never coming up as 98.6, right? And you might also notice that your internal body temperature is not even 98.6 if everyone runs differently. But even if you summed up, if you took the average of all those numbers of the temperatures that you took every single day, they're going to look like, they'll be all over the place, right? On some days, you'll get 96.1, 98.9. They'll be basically like all over the place. Who knows? Sometimes you're hot, sometimes you're cold. And it could be the case that the average of these is actually is nowhere close to any given observation. So you saw theta hat at each day, and you saw an observation each day, and the average of these is nowhere near any of them. So the average could actually be quite far away from the actual observations. This happens if you have, like, say, bimodal data. If you have two sort of humps in the data, the average of the data is nowhere close to anything. And so what you might be interested in is how close, for any given theta hat, how close is that going to be to the expected value? And to justify that, we need to define the variance. And the variance is just this quantity that I hope you're all familiar with. Basically, it's just the square deviation from your expected value. And in our case, we had that the expected value is equal to theta star, which is great. That's not always true. But now we have that the variance is equal to this quantity. And as a rule of thumb, the variance of this estimate theta hat MLE is basically equal to its expected value plus or minus square root of the variance. How do we justify that? We can justify it on the next slide. But as an exercise, maybe not now, because we're running a little behind schedule, I'd like you to, maybe after class, go ahead and compute the empirical variance. I think this is actually a part of homework 0, or something very similar to it. And the way that you do this is basically recognizing that writing theta hat in this form of a sum of indicators, where each indicator has a probability of being whose expected value is equal to theta star. And you can compute that variance quite easily using what you've already done on homework 0 in abstract. And so you can do this. And to get more precise, but that still is pretty imprecise, because, I have this squiggly line here. What does that mean? It doesn't really, this is basic rule of thumb. To get a little more precise, you can talk about how things happen in high probability. So you can say, well, on any given run of this algorithm, I run my theta hat MLE. How likely is my theta hat to deviate from the expected value that I expect to see in each time? And what we can do is we can use something called Markov's inequality to show this. And we can say, what we'll be able to say is that with probability at least 0.99, theta hat is no more than, say, a square root of the variance away from its mean. There's someone just asked in the chat, I saw that it does, when I say approximate here, do I mean like convergence of probability or congruent or anything like this? No, nothing that's fancy. I'm just saying that it's approximately. When I do wavy lines, it means approximately. And I very explicitly, I'm being like, this is very hand wavy. And don't, is a rule of thumb. This is how much you kind of expect, sorry. Theta hat is equal to this. The value of theta hat is going to be around its expectation, and it's going to deviate about the square root of its variance away. Yes. So there's a great question in the chat right now. When we take the expectation of the MLE, what is the randomness that we're taking the expectation with respect to? What is random here? The randomness is the random sequence of heads or tails that we saw. We have a sequence of n heads or tails, but like on any given day, I could have, if I have, on every day I wake up and I flip a coin n times, I'm going to get different numbers of heads each day. And so what this is saying is, when I take the expectation, this is expectation with respect to that random number of heads or tails that I see on any particular day. And I'm averaging over all those possible sources of randomness to get this expected value. And so while theta hat MLE is random, it's a random variable, this is random. The expected value of theta hat MLE is deterministic. It's just a number. There's nothing random about the expected value of theta hat MLE. It is just a number like 5. It is not, whereas the theta hat MLE is a random variable. It is a complex object, not complex in the imaginary number complex, just complicated object. It has lots of structure. The expected value of that random variable is just a number. It is a scalar. There's nothing random about it. Okay. And so we can use Markov's inequality again to say the probability of the probability that the mean, the value that you see deviates from its mean plus the standard deviation, or the square root of the variance, is less than something with some probability. And this is, we can use Markov's inequality to make statements like the value that you'll see will never deviate more than 0.1 away from its true value, with probability at least 99, 0.99. So that we can trust, you're quantifying how much things actually vary. And this is not, there's no expectations here. It's really just like saying the value that you see on this particular day will not vary more than this on any particular day. And so I have an exercise here. You can try to work it out after class, or we'll put something on the homework that's similar to this, so you can work out these exercises. So just sort of conclude what the general model or the algorithm for maximum likelihood estimation. We are in general going to assume that we observe some n sequence of random variables, x1 to xn. These can be they can be scalars, or they can be vectors, but they're just random quantities. But we're going to assume for each xi is IID. Meaning each one behaves the same as any other one. They're all drawn from the same distribution, and they're all independent. And then we're saying they're all independent from a distribution f of x theta. And this f of x theta is the probability of observing that x given theta. If you're looking at densities, we're just looking at discrete objects now, so f is the probability mass function. So x can take values of heads, tails. But if it's a real value, which we'll see in a moment, then f of x theta will be the probability density function. And so you have the data is drawn IID from some density or some probability mass function. F, in our case, it was theta, or 1 minus theta. You write down your likelihood function, which for us was this theta times 1, theta to the k times 1 minus theta to the n minus k. You take the log likelihood of it, and again, this step, taking the log likelihood, is really just a mathematical convenience. Typically, because the likelihood will always be a product of things, the log of it will always be a sum of things. It's always easier to work with, or almost always. And the maximum likelihood estimator is this argmax of the likelihood or the log likelihood, whichever one is easier to work with. And typically how we do that is we set the derivative equal to 0 and see where it's maximized. But we're going to see very shortly where that's not going to be possible, where there does not exist a closed form solution. Okay. So this is the general algorithm, and for some practice, we're going to see a different case real quickly. We're going to see the case of what about continuous variables? So we just talked about temperature a minute ago. What if you have, those aren't discrete values. Those are, taking values 98.1, 98.6, 96.5, whatever. They're somewhat real values. They're coming out of a thermometer with some amount of decimal precision. And so a natural sort of distribution or model that we can place on the space of temperatures may be a Gaussian distribution. Is this perfect? Well, no. If you're measuring things in Celsius, they can't get below negative 273. So it's not perfect, and Gaussians have infinite tails. But it's a pretty good model. And as George Box said in 87, all models are wrong, but some are very useful. And Gaussians are one that are very, very useful. And how Gaussians work is they're defined by a mean and a variance. And so what they look like, they are the, what we're all familiar with, the bell curve. It is centered at a mean mu, and it has a width of sigma. Okay, it is just your standard bell curve Gaussian random variable or normal distribution. The standard normal, where you'd have mu is equal to 0 and sigma equal to 1, but in general, the Gaussians are defined by their mean and their variance. There's lots of nice properties of Gaussians. These are all reviewed in the book. If any of this is unfamiliar with you, please go read the book. It's chapter 2 of Murphy, and you'll get caught up on these kind of details. These aren't important for what we need to use them for, but it's just nice to know these. Linear transformations of a Gaussian. So ax plus b, where x is Gaussian, is just another Gaussian. The sum of Gaussians is also Gaussian. Difference of Gaussians is Gaussian. All these sort of things should be sort of familiar to you. Just some properties of Gaussians. And if not, I'd highly recommend you go and do some practice. So if we follow the recipe of maximum likelihood estimation for Gaussians, what we observe is some data. And now our data can, instead of being heads or tails, now it's real numbers. So it can be 1.5, 2.5, 98.6, 97.3, etc. We just see some numbers. And then to construct our likelihood function is the probability of seeing the data given a given theta, or our unknown parameters. In this case, our unknown parameters are mu and sigma. We don't know the mean, we don't know the sigma. We don't know the spread of this data. And so if we just write this down, and we take under our IID assumption, the product of the joint is equal to the probability of the joint of all these random variables is equal to the product of each one individually. And that's why we can get, this is just equal to the product of I equals 1 to n, or the probability of xi given mu sigma. And then when we plug this in, that probability distribution on the last slide, we get this expression here. And now the log likelihood of this data, again, always saying the log is convenient. We take the log of it, and we get this expression as follows. And so now what you're wondering is, okay, if I call theta, if I just say that theta is equal to this tuple, or this vector, which includes mu and sigma squared, what is the maximum likelihood estimate? We can do it computationally, but there's also a very nice picture here, right? I want you guys to think about what you're doing whenever you're talking about what is the maximum likelihood estimator of something, right? Because the picture is very, very interpretable. So let's say we observe some data. Our data was equal to, let's say, 4.5, 5.3, 4.8, blah, 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 right? Some amount of data. And so we've got, 4.5, 5.3, 4.8, and so on and so forth. We see lots of data. Okay, each one of these little lines denotes like one data point, let's say. Now, if we're trying to figure out what is the likelihood of this data, let's look at this form. Look at the likelihood function of this data. It's a product of a bunch of little bumps. We know that each individual bump looks like this, right? Each one has this form that is equal to just this little bump. And just like we had with the Bernoullis, if I take the product of these, they're also going to look like a bump. Okay? And what we're really trying to do is say, like, well, I'm trying to maximize this probability of this data. But another way of interpreting this, instead of being in mu and sigma space, we can say is, for any probability of x given mu and sigma, I can now vary mu and sigma and see what kind of distributions I'm going to get out. One mu and sigma could be like this. Right? Maybe this would be, maybe this one is mu equal to 0 and sigma equal to, I don't know, 3. Then there'd be another one that's over here that's like, that's supposed to be a Gaussian, mu equal to 8 and sigma equal to, let's make that really, and sigma equal to like 0.5. Okay, but then there's this other one that's like right here, and this one's equal to mu equal to 4.7, let's say, and sigma squared, and sigma equal to let's say 2. Right? And of these 3 choices, clearly what we're doing is the product of the likelihood of seeing this data given a mu and a sigma is just producting all of them. So it's evaluating each one of these black points on this surface, like on this green surface, or this orange surface and blue surface, and then multiplying them all together. And so what you really want to do is you want to change mu and sigma around until when you evaluate each one of these points on this function and take the product of all of them, it's maximized. And so the reason why orange would be a terrible function or a terrible choice is precisely because it's placing on all these guys on the left-hand side, it's giving zero, is giving basically 0. It's very, 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 very small value. And it's producting everything. And so the product of a very small number times any other number is a very small number. Whereas green is somehow balancing it. But if I make it too broad, then what happens is that this Gaussian gets flatter. So this is a little, because sigma is equal to 3 here. Well, let's say sigma is equal to 1. So if sigma is equal to 1, it's a little, thinner and a little taller. And so the sigma defines the height and width of this thing. And so what we're trying to do, what the MLE is doing is it's moving sigma and mu around in order to maximize the probability of observing this data. And it's literally just evaluating the likelihood function at each individual point and multiplying them all together. So that's what's going on in the picture. How does it work in the math? In the math, we do exactly what we did before. We take the derivative, we define the log likelihood, it's equal to this, I just copied it from the previous slide. We take the derivative with respect to mu, and what we get is something very simple. All we get is, this is just going to be equal to the sum 1 to n. There's no mu here, so that's just derivative of that is equal to 0. So I just take the derivative of the second term. Take the chain rule, the 2 comes down, cancels the 2 in the denominator. Using the chain rule, I have the minus 1 on the mu comes outside, and then we just get xi minus mu over sigma squared. And then what we do next, we set it equal to 0, and then we solve for mu. And what you're going to find, just rearranging things, the sigma squared doesn't matter. It's completely independent. If I multiply by sigma squared on both sides, it just cancels. And so for any sigma, we see that the mu hat MLE is equal to 1 over n times I equals 1 to n of xi. Right? A very intuitive result. The mean of the Gaussian, we're trying to estimate the mean of this Gaussian, and we assume that data came from a Gaussian with some mean mu and variance sigma squared. The estimate for the mean is just the sample average. A very sort of natural and intuitive estimator. For the variance, you do the same exact calculation, but now we're doing this but to sigma, right? So now we have a sigma in this first term, but the log of x with respect to x, just 1 over x. And so this is going to be negative n times 1 over sigma square root of 2 pi. Chain rule, times 1 over square root of 2 pi minus it's just this guy down here. So the derivative of 1 over sigma squared is equal to xi minus mu squared. It's going to be either as 1 over sigma squared is equal to sigma to the minus 2. So it's a minus 2 sigma to the minus 3. And now multiply by sigma cubed on both sides. And we get minus n times sigma squared plus the 2's cancel here, the minuses cancel. Squared. That's the derivative, setting it equal to 0. Well, we would have set it equal to 0 on the last line, because you're trying to find this with respect to 0. After setting derivative equal to 0. So equal to 0, and we find that sigma squared is equal to 1 over n, I equals 1 to n, xi minus mu squared. And this is our MLE estimate. And now we get a little confused, right? Because the right-hand side depends on mu. We don't know what mu is, right? Mu was something that we're trying to estimate in the first place. So our estimator of sigma hat MLE depends on the value of mu. When you computed the mean, this didn't happen. When we computed the max likelihood of the mean with respect to our data, the answer just came out with respect to the data and didn't depend on sigma. This can sometimes happen. And that's why we have to think about it. That's why it's helpful to think about this picture of what are we actually doing. We're moving mu and sigma squared around until it maximizes the value of this likelihood. And so if we're thinking about this as a 2D maximization problem, we're maximizing over mu and we're maximizing over sigma squared. What this is saying is that the maximizer with respect to mu is going to be the empirical mean. It will always be the empirical mean. In the maximizer with respect to sigma squared, it has to do with this expression of mu. And if you think about what's going on here, where is this expression going to be maximized? It's going to be maximized exactly where mu is equal to mu hat MLE. And the way that you deal with this formally is we have to actually, that's sort of a heuristic argument. And it requires some sort of thinking about where is this thing actually going to be maximized? Because for any sigma, mu hat MLE is going to be the maximizer at that mu. And we're maximizing with respect to mu and sigma. They're both variables in this optimization. We're maximizing both of them. And what this is saying is that the maximum, where is mu maximized for any sigma, it's equal to mu hat MLE. And so what we conclude is that this is equal to I equals 1 to n xi minus mu hat MLE. Because this optimization was being done really jointly with respect to mu and sigma, and for any sigma, mu hat MLE is the maximizer of this log likelihood function. And so to go through that, I encourage you to draw a picture of what's actually going on in spaces where the x-axis is mu and the y-axis is sigma squared, and realizing that for any choice of sigma, you're going to have that mu as a maximizer, and you'll end up with this solution. And so what we conclude is that for the Gaussian, we have that mu hat is equal to this quantity, and the sigma squared is equal to this quantity here. And one thing I encourage you to work through exercise. If you work through this, you'll find that if you take the expected value of the variance, this estimate for the variance, you'll find that it is not true. It is not equal to the true variance. So we saw, on our previous example, we saw that the expected value of theta hat MLE for the coin was an unbiased estimator of the true value. What we're seeing here already in our second example, the maximum likelihood estimator of the variance is not equal to the true variance. And so it's a biased estimator. And one can show that if you use this estimator, is an unbiased estimator. And all that means is that if you take the expected value on both sides of this estimator, you'll find that it is equal to sigma squared, the true variance. And what we'll go through over the next couple of weeks is why would you ever want a biased estimator? And we will really go through that in detail, deciding when you do something biased, when you do something unbiased, and so forth. And what are the properties, what are the trade-offs there? And so again, just to wrap up this lecture, maximum likelihood estimation is totally general. It can work, I've just shown it for Bernoullis and Gaussians, but it can work for any kind of data. So if xi's were drawn from the exponential distribution, say, with parameter lambda, so that the probability that xi greater than t is equal to e to the minus lambda t. There's an exponential random variable, so it means that like the distribution looks like this. They're positive. You can do a maximum likelihood estimate and try to figure out what that lambda is if you observe this data. It's a completely general algorithm for doing an estimation of a procedure if you're given data. You're trying to estimate what are the parameters of the underlying distribution that you wrote down. How did you model the world? How did you model the data that generated this data? And then you're trying to estimate those parameters given that model. And the MLE is a way to do that. Some other things, some properties that I don't expect you to memorize or anything like this, but just so you know, the MLE has a lot of very nice theoretical properties. You can show that it's asymptotically consistent if you normalize by the standard deviation under very benign conditions like the smoothness of the log likelihood function. And it's also, in some sense, optimal, asymptotically, anyways. It has a minimum variance, meaning if you have the maximum likelihood estimate theta hat MLE for some theta, which could be a vector of parameters theta, basically what this is saying is that the Kramer-Rao lower bound says that the MLE, if it is unbiased, if it is an unbiased estimator and is the MLE, it achieves the Kramer-Rao lower bound, which is basically it is the minimum variance estimator out there. So that you have any possible estimators out there, and what the MLE satisfies is, at least asymptotically, there's no other estimator out there that can achieve a smaller variance than the maximum likelihood estimator. And so in some sense it's optimal, but only asymptotically. But it's very good evidence to suggest that the maximum likelihood estimator really is a great idea, and that you should be using it. So it's the first step, it's the first estimator that you should always try, and that's why it's the first lecture. And so to conclude, what the learning problem here was, this class is called machine learning. What was the learning? Where did we learn? What learned? In this sort of recap, this would become much more sophisticated over time, but what we did is we collected some data. And maybe at the same time, simultaneously or before, we chose a hypothesis class or model for how this data was generated. Really, this should come before. You should decide how the data was generated before you saw data. And then you're going to choose some loss function, like a likelihood function or a reward function. And you're going to optimize that procedure. You're going to choose the maximum likelihood estimate. And then you're going to justify the accuracy of this estimate using the variance, or you're going to use Markov's inequality for a probability estimate, so that you're not only giving back an answer that's a point estimate, you're not just saying 3/5, you're saying, I believe this coin is 3/5, and the error bars are plus or minus 0.1. in standard deviation or in high probability or something like this. And that's going to be a trend throughout this entire course. Is we're not going to ask you just for an answer. I want you to justify that answer at every step. I want you to be able to give an answer and be able to say why that is the answer and what is the accuracy, what is your certainty in that answer. Okay. And I've taken the entire time for this. I apologize, Jamie.
No, that's quite all right.
And now, I'll leave the last few minutes for questions. Either. I see here, one of the questions is, what is hat SE in this previous slide? This is the standard deviation. So this is the square root of the sample variance. But the sample variance is defined as something like this. It's something analogous to this, where the data d-mean by its empirical mean and average. Sahil, you had a question?
Yeah, can you hear me?
Yep.
I was just wondering, for what kind of data would MLE not work?
That's a really good question. So it really requires, one of the big assumptions for MLE being a good estimator is something called a concept known as identifiability, or strong, basically, when does the data actually give you an estimate that is actually pinning down what the answer is? And why this is important is because a lot of times what can happen is that your model that you're looking at is so high dimensional, your model has so many parameters, and you observe some number of data points that isn't enough. You know, you just don't have, like, let's say you have 100 parameters in your model. It's modeling how COVID-19 basically evolves over time in the Seattle area.
And it's the function of potato chips purchased, for example, right? It has like many variables.
Yeah. Any number of something with lots of variables, and you only observe 30 examples. You only observe 30 data points. Now, you're not going to be able to estimate 100 parameters with just 30 data samples in general. And in these sort of situations, what you actually want to do is bias yourself towards solutions, because what's going to happen is that if you're limited to a small amount of data, there are some solutions that are more likely, or that you believe in more likely to occur, like what you actually think the data is like, and you try to bias yourself towards those positions. And the MLE typically will basically not be able to be satisfied in those situations. And so we'll see examples of this in the future. And so please ask this question again. Where will the MLE fail? And we'll see that again.
Thank you.
And you should always, sort of as Kevin suggested, right? Like, using the MLE is usually a good idea. And you should always ask yourself, if you're not using the MLE, why? It's sort of the first estimator you should always try, unless there's some reason it is not a good idea, right? And Kevin this time was talking about sort of one example where that's the case. In general, you should always try the simplest thing first, and like only vary from it when you have a good reason to, right? And something similar will happen with what we'll talk about on Monday, which is talking about linear models, right? So like, you should always start with a linear model unless you have a good reason to believe that a linear model is not enough, right?
Okay. Thank you.
Okay, sorry, there's a lot of questions here.
Okay.
It's a question here. Can you...
Kevin, I can help answer part of the questions.
Okay.
I'm working on chat.
Okay, well, I'll just try to answer these as they come as well. Can you elaborate on biased and unbiased? What I mean is that in Estimator, so the true value in this case, so that we believe that the data came from a true value that's equal to theta star. Like there is a probability of heads equal to theta star that is actually true that we believe. And now we say that a value is unbiased if theta hat MLE is unbiased if the expected value of theta hat MLE is equal to theta star. If it is not equal to theta star, then it is biased. And basically what this means is basically the theta hat will find that theta hat, by Markov's inequality really, does converge to its expected value. And so if its expected value is not equal to theta star, this means even if you get an infinite amount of data, it will never converge to its true value if it is biased. And so like the MLE, if you're using a biased estimator, you should really ask yourself why. There might be a good reason, but if your estimator is biased, you should really be asking yourself why that is the case and sort of check yourself. The question, why are we using Markov's inequality given that it is a loose bound? It's because it's remarkably simple and very easy to prove, and kind of a core sort of inequality to drive all the other tight inequalities that we might look at later. Non-IID data, that's a complicated question. Really, when you leave the IID world, you have to be very careful about what you mean when your data is not IID. Basically, you need to write down or justify more what you actually mean if your data is not IID, because I don't know what the probability of heads is in that case. So that's definitely handled, but it requires, you can only answer different questions with that. You can't talk about probabilities typically. You have to talk about maybe beliefs, or you can talk about quantities of interest that you care about, but not necessarily, it's just different model assumptions.
Kevin, someone asked a good question. Why do we want to minimize the variance of our estimator?
That is a good question. So, well, the variance of your estimator is this quantity here, and is this expected value of the squared deviation from what you expect your estimator to be. And so it's basically the spread you expect to see. It literally is in expectation, how much do I expect my estimator to be away from its expected value? And we ideally want this to be small, because we'd like to have the spread of our function to be small. And the reason why we like the variance to be small, again, is because this sort of hand wavy argument that as a good rule of thumb, your estimate is always going to be about its expectation and of some deviation plus or minus the square root of its variance. And this is under some subtle conditions or benign conditions that Markov's inequality can illuminate. If you go through this sort of exercise, you will find that it can justify this squiggly on this slide. But then basically that is why we like the variance. The variance is basically really telling you how much will the estimate that I see vary away from its expectation. Another good question to see is, how do I know what parameterized distribution my data comes from if I'm going to use the MLE? You just pick one based on modeling assumptions. This is a very, very good assumption, a very, very good question. In both these cases, we had Bernoullis and Gaussians. And Bernoulli data, like for these coin flips, that's pretty reasonable. If you see zeros and ones, that's, having a Bernoulli data is pretty reasonable. But when I introduced the Gaussian data for temperatures, I said right in the beginning, this is just an approximate model. It's not perfect. It's not great. And if that model were wrong, like, if it were not a good fit, this could be a very, very bad thing to do. And so basically the estimates that you produce are only good as the model that you write down. And so writing down the right model is critically important. And so what we'll find is that we will be able to loosen some of these assumptions by asking different questions. This is interested in saying we wrote down a model and we're trying to estimate the parameters of that model, assuming the model is correct. But what you could also do is say, well, I don't care about what the actual model is. I just want to have a good predictor. I just want to be able to predict if an image has a cat or a dog in it. I'm not trying to I'm not saying that my model is like the true, whether there's some true notion of a dog or a cat in a model or in the image. I'm just trying to predict whether it's a cat or a dog in this picture. And in that case, we'll be able to loosen these assumptions, and we won't have to write down any strong models like this. But we will still have IID. And what we'll be able to say is we assume that our data is independent and identically distributed according to some model, but we don't know which model, or some probability distribution, but we don't know that distribution specifically. And we can still say things like this. And so over this course, we'll be able to say stronger statements like that. It's a great question.
We've got a hand from Chefen.
Hi. Let's say we don't have IID, but instead we have like a simple situation where we have like a bag of balls and we're taking a ball out every single time and just recording the color. So when we don't have replacement, how do we do can we apply this maximum likelihood estimation to that scenario? Hello? Hello?
Is he muted?
Hello?
I think he's muted. Or wait, no.
He's muted.
Can you hear me? Yeah. So my
iPad appears to have crashed, so that's awesome. At least it happened at the end of lecture. Okay, so there's a question about Polya urns, about how, like, if I had if the urn started with 10 black balls and 12 white balls, and I take a ball out, and if it's black, I put that ball back, and also another black ball, and I do this for a long time, and same thing with white balls, and so that's a dependent process over time. And then maybe after I run this process for a long time, I look at the total number of black balls, the total number of white balls, and then I determine what how many black or white balls were in the initial conditions. What was the initial starting condition of this urn before we started this process? Yes, you can write that down as a maximum likelihood estimate. You can do that. It would be incredibly complicated because you can do it. It would not be IID. You can write down the probability of any given because at the end of this process, if you did this for T trials, then you can deterministically know how many balls are going to be inside the urn. You just don't know what the distribution of whites and blacks are. And then you're going to, based on these T observations, try to determine what the initial conditions were. You can write down what the probability of every possibility of the number of black balls and number of white balls is after those T trials. there's some, you can write down the likelihood of that those numbers given those initial conditions. You can do that. I would, that might be very, very complicated. That expression can be extremely complicated. And so typically, when we talk about dependent processes like that, we adopt different tools, typically tools from martingales, in martingale theory. And this is what allows us to say things, bound things in different ways. Sometimes you get lucky and it's easy. This process is easy to understand. You can do maximum likelihood. So I guess what I'm saying is, yes, you can still do maximum likelihood under these non-IID assumptions, like you said, because we can still always write down the probability distribution that generated the data, and then maximize that likelihood given the data. Maximize the probability, maximize this probability of seeing the data given those initial conditions. Maximize it with respect to the initial conditions. You can do that, and it would be non-IID data, but it could be a very complicated expression. And so we typically will use different tools to analyze those situations. It's a really great question.
So moving forward, we'd most likely use MLE for IID situations, just because it's more easy to use. Okay.
Yeah, I doubt we will ever see anything in this class that is not IID. It's kind of one of the core tenets of machine learning, at least like basic machine learning, or like, you know, anything you've seen in machine learning is basically IID. Or the sort of the examples that you see with recommendation systems and things like this, like Spotify or stuff like this. Where you don't see that is when reinforcement learning, say like Go or a computer playing StarCraft. That is reinforcement learning that is non-IID, and that's a completely different course.
And just one quick mention, which is that IID actually has like two parts, right? IID has independent and identically distributed. So I saw it came up earlier in the chat, and it's also a part of this question. Independence is like a really strong assumption of those two. So if you have a process that is not identically distributed each time, but it is the case that like the observations you have are independent, a lot of the same techniques do push through fairly smoothly. But when you have non-independence, when things are dependent, that's when things tend to get much messier.
Thank you.
We have a hand from William. I know we're getting a little over time here.
William? William, you want to unmute and ask your question? Maybe not.
Hey, can you hear me now?
Yes.
Oh, great. So I just wanted to add on to the last discussion about kind of minimizing the variance. Does that just relate directly to like the bias-variance trade-off?
Yeah. Yes. So we'll be covering that over the next few lectures. And basically, in any kind of estimator, the variance is defined with respect to the expected value, right? So it is the deviation away from its expected value. So if the expected value is biased, then your true error is basically the variance, the total deviation away from the truth is going to be the variance plus the bias squared, is what we'll see. And so you have to, a good estimator balances these two, balances the variance with the bias.
Okay. But when we're talking about like variance as in overfitting, is that the same variance as like the standard deviation or?
Yep.
Okay, cool. All right, thank you.
We have a hand from Tim.
Hey, Tim, what's your question?
Yeah, thanks. Just clarifying about the intuition. When we have the Gaussian case, the probability that we would see the data is 0 because it's continuous, the specific data. So is the intuition just to think about sort of a limit of small neighborhoods around our observed data points as those interval sizes go to 0?
The intuition should be you're evaluating the density. So the likelihood really is honestly, like, the likelihood function is equal to the probability of observing data given your parameters when you're in discrete distributions. When you go to continuous distributions, you're absolutely right. The probability of seeing any one sample from a Gaussian is equal to 0. But you can still talk about the likelihood of observing that data, and the likelihood of observing a data point given parameters is defined as evaluating the density function. And the densities and the probability mass functions are equal to each other in the case of discrete random variables. But in general, it's going to be evaluating the density function.
Okay, thanks.